Hello everyone. In this session, we are going to solve problems on permeability. We have seen in earlier classes what is permeability, its dependency on other properties of soil, as well as a mathematical approach how to determine permeability in variety of types of soils. So with that idea in mind, we'll start. This is problem number 1. It's taken from the question paper itself. We shall read it. The results of constant head permeability test on fine sand are as follows. Area of the soil specimen 180 centimeter square. Length of the specimen is 320. It's a constant head maintained at 460 mm and the flow of water through the specimen 200 ml in 5 minutes. Determine the coefficient of permeability. Here it's very clearly mentioned that it is a constant head permeability test. That's why we have a ready-made formula, that is K equal to QL by ATH, where Q is the quantity of water collected in time duration T, right? So we have all the data that is given. Area, cross-sectional area of the soil is given, length is mentioned, this is in centimeter square, this is in millimeter. You have to convert that into centimeters so that homogeneity of the units is maintained. H, the head lost, is 460 mm, 46 centimeter. Quantity of water collected is 200 ml in 5 minutes, that is 300 seconds. So if you substitute everything in centimeters and seconds, the K comes in centimeter per second. So here it is 200 cc into 32 divided by 180, 300 seconds, 46 centimeters. So everything reduces to 0.00258 centimeter per second, or 2.58 into 10 raised to minus 3 centimeters per second, or 2.58 into 10 raised to minus 5 meter per second. That's how the K is written. K has got units of velocity. K is defined as the velocity under unit hydraulic gradient, because you know that it is defined with taking this Darcy's law as the basis. So K is nothing but V when I is equal to 1. That's how the K is defined, coefficient of permeability. Okay, we'll go for the next one. Problem number 2. Okay, the discharge of water, if you read it, collected from a constant head permeability. So again it is very specifically mentioned that it is constant head permeability. In a period of 15 minutes, T equal to 15 minutes is 400 ml. 400 ml is quantity of water. The internal diameter of the permeameter is 6 centimeter. So cross-sectional area is not directly given, but it is given. Okay, the permeameter is 6 centimeter and the measured difference in heads between the two gauging points is 15 centimeter apart, and it is 40 centimeter. So here L is equal to 15 centimeter and then H equal to, the head lost is 40 centimeter. Calculate the coefficient of permeability. Calculate the coefficient of permeability is K. If dry weight of the 15 centimeter long sample is 7 newtons and the specific gravity of the solids is 2.65. Calculate the seepage velocity. Seepage velocity, that is superficial velocity. Okay. Now, so T is 15 minutes, 900 seconds. Q, the collected water is 400 ml, 400 cc. Internal diameter is 6 centimeter. Area becomes pi d squared by 4, 28.27 centimeter square. L, the length is 15 centimeter with h equal to 40 centimeter. So K equal to QL by ATH. If I substitute everything in centimeters and seconds, I'll be getting 5.896 10 to minus 3 centimeter per second as the value of K. Now V is equal to Q by A. This Q is 400 cc divided by cross-sectional area is 28.27. So if you know that, the velocity of the flow is given to be 14.15 centimeters square. Centimeters per second. So this is superficial velocity. Now we know V is equal to N into Vs, or Vs equal to V by N. So seepage velocity, which is a faster velocity, that is Vs, is V by N. But we should know N. With the data given here about the sample, we can calculate N, use that N to find out Vs. How I have done, I'll show you. Now volume of the specimen is 28.27, which is cross-sectional area multiplied by the length of 15, 424.1 cc. So gamma dry is nothing but weight divided by volume. Weight is given to be 7 newtons. Volume is 424.1 cc. So many newtons per cc, or if you convert this into kilonewton per meter, it will be 16.51 kilonewton, because newton has to be divided by 10 raised to 3, whereas each of these centimeters have to be divided by 10 square. So overall it will be 10 raised to 6 on the top and 10 raised to 3 in the denominator. That is to say 10 raised to 3 in general. So if you do that, it will be 16.51 kilonewton per meter cube is dry density. But dry density is given by G gamma W divided by 1 plus E. Hence E can be calculated. E is 0.575 and N is equal to E divided by 1 plus E. So that's why it is 0.365. Now Vs, velocity of seepage, equal to V divided by N, 14.15 divided by 0.65, 38.78 meter per second. Okay. Okay, in this third problem, it's also from the question paper. In a falling head permeability test on a silty clay sample, the following results were obtained. Length of sample is 12 centimeter. The diameter is 8 centimeter. Diameter of the standpipe is 0.4 centimeter. Initial head in standpipe is 120 centimeter. Final head is 40 centimeter. Time of fall is 6 minutes. Find the coefficient of permeability of the soil. Very straightforward data. Clearly mentioned that it's falling head, and then why falling head, they have mentioned it's a silty and clay sample. So with this, if I try to calculate cross-sectional area of the soil with the diameter 8 centimeter, it is pi d squared by 4, 50.27 centimeter square. Diameter of the standpipe is 0.4. Because of that, this lowercase letter a of this equation is pi d squared by 4, 0.1257 centimeter square. So for falling head, k equal to 2.303 AL by AT log to the base 10 H1 by H2. I'm taking log to the base 10 because I'm multiplying with this. If you are not multiplying, then AL by AT log H1 by H2 to the base E. So if you substitute 0.1257 for this 12 centimeter, for this 50.27, for this 6 into 60, H1 is 120, H2 is 40, and simplify, we'll be getting 9.16 into 10 raised to minus 5 centimeter per second. So if you look at the style of the problems, they are very simple. They have got an equation, and sometimes they may ask you what is the time required from t unknown to go from particular height to particular height. Like that, questions can be designed. Okay, let's see the next one. Okay, another. A falling head permeability test is performed on a soil sample whose permeability is estimated to be about 3 into 10 raised to minus 5. So here K is given. What diameter of the standpipe should be used? So lowercase letter d or A is asked. Is if the head is to drop from 27.5 to 20 centimeter in 5 minutes, and if the cross-sectional area and the length of the sample are respectively 15 centimeters square and 8.5. This is first part of the question. Will it take the same time for the head to drop from 37.7 centimeter to 30 centimeter? Here there is a difference of head of 7.7 centimeter, whereas here there is a difference of 7.5 centimeter. Now can you guess which time will be more? If you have a judgment, if you got higher heads to drop, it will take lesser time, and same difference if it is there with lower heads, it may take longer duration. Right? That is what we will be getting anyway. In a usual manner, if you go on writing the data and then substitute into equation, let us see what happens. The length is given 8.5 centimeter, cross-sectional area is 15 centimeter square, time to fall 5 minutes, H1 is 27.5, H2 is 20 centimeters, so K equal 2.303 L by 80 log to the base 10 H1 by H2. Substitute. The only unknown in this is this A, because K is given 3 into 10 raised to minus 5. Keeping all the things in centimeters, we get A equal to so much. Our diameter of the standpipe is so much, 2.52 mm. 2.52 mm is too small tube that is required. Okay, second part of the problem. H1 is 37.7, H2 is 30. Calculate the time. Now, keeping all other things, because A is now found, right? So substituting at so many centimeters square and then evaluating, T comes out to be 300 seconds. That is it has taken 5 minutes. Okay, though there is a more drop, it has taken the same time. That is what we can observe, because the time drop, the length of the drop is 37.7 minus 30 in the sense 7.7 centimeter, whereas here it is only 7.5 centimeter, but time taken is same. Okay. sorry, the calculation is given you 215.22 seconds, which is less. Obviously it is less time. Okay. There is a printing mistake. A stand no, a sand deposit of 12-meter thick overlies a clay layer. The water table is 3 meters below the ground surface in the field of permeability. Pumping out test. The water is pumped out at a rate of 540 liters per minute when steady state conditions are reached. Two observation wells are located 18 meter and 36 meter from center of the test. The depth of drawdown curve are 1.8 and 1.5 meter respectively for those two wells. Determine the coefficient of permeability. Okay, data if you go on writing, it is a case of unconfined aquifer, expression for which is k equal to 3.303 q divided by pi z2 squared minus z1 squared log of r2 by r1 is 10. Now here the data given, if you look at, r1 is at a distance of 18 meters, r2 is 36 meters, h, right, you have 12 meter minus 3 meters because thick layer is 12 meter, order table is, so initial depth of water is 9 meter. This will not be used in the equation anyway. D1 is 1.8 meters, the drop. D2 is 1.5 meter. So I have to calculate Z1. There is a figure also, I think, okay, here, okay, sorry. So this is 3 meters, that's why this has become 9 meters. Now this is 18 meters, the first well. The other one is 36 meters. Here there is a drop of 1.8. Here there is a 1.5 meters. So drawdown curve depths they have given. So we can calculate Z1, Z2 becomes 7.2 meters and then 7.5 meters. Now if you substitute and simplify, we'll be getting 4.594 10 raised to minus 4 meter per second. Okay, a pumping test carried out in a 50 meter thick confined aquifer, very clearly mentioned confined, results in a flow rate of 600 liters per minute. Drawdown and two observation wells are located 50 and 100 meters from the well are 3 meter and 1 meter respectively. So if this is 3 and this is 1, so in a 50 meter, this is 50 plus 20, they have given all this. 50 meter is this plus 20 meter, so permeable layer is confined. So there is a 67 because there is a 3 meter 1 meter drop, that's why there is a 69 meters. Now if you calculate with a equation which is meant for a confined aquifer layer, just substitute everything properly, you will be getting this. The next problem, again it is a falling head permeability test. Length and area are given. Calculate the time required for it to drop from 0.25 meters to 0.1 meter. Standpipe area is given. The sample has 3 layers. Okay, there are 3 layers having permeabilities 1, 2, 3, and for third layer it is 6 into 10 raised to minus 5 meter per second. For third, 0.05 meter height, means they have given coefficient of permeability and their thickness. Assume the flow is taking place perpendicular to the bedding plane. So it is a flow in a stratified soil with the direction of flow perpendicular to the stratification. Moreover, it is a falling head permeability test. So with the given data of strata and coefficient of permeability, we have to find K equivalent first of all. Use it for falling head permeability test. Okay, so we'll do that. Falling head test with L, A, T is required, H1 to H2, A equal to so much. Okay, now sample has 3 layers. Flow occurs perpendicular to the plane. And then what are the data points given? K1 is 3 into 10 raised to minus 5, H1 is 0.06, like that. There are 3 layers. So the total thickness of 3 layers is H equal to 0.17 meters. So when the flow is perpendicular, H by K equivalent equal to H1 by K1 plus H2 by K2 and so on. So K equivalent is equal to this H divided by this whole expression. So I substituted for that everything and simplified. So this is equivalent coefficient of permeability 39.23 into 10 raised to minus 6 meter per second. Now using falling head permeability test expression 2.303. So this is A capital L capital A T log 25 to 10. This which units you use is not a matter because it cancels off. So you are getting K I have substituted from here. The only unknown in this equation is T. If you find, you will be getting it as 6.07 minutes. So it is combination of stratification plus falling head permeability test. Okay. Next, a soil profile consists of 3 layers with the properties as shown. Calculate equivalent permeability, parallel and normal to the stratum. Both are asked. Simple data points are given. Thickness of the layer, coefficient of permeability. So if you have parallel to the layers flow, then equivalent horizontal, equivalent actually parallel to the flow. Expression is this. Substitution, simplification gives you 9.62 10 raised to minus 6 meter per second. If the flow is normal to the stratification, expression is this. Substitute everything, simplify, you'll be getting 1.23 into 10 raised to minus 7. What you can observe here is this, when the flow is perpendicular to the stratification, the K is quite less compared to the K parallel to the stratification. Okay. Okay, with this we'll stop. Thank you.